series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Professor Ravindran. He will be speaking on modeling paradigms and tools for autonomy management in complex networked systems. Professor Ravindran is a professor of computer science and data science at the Grove School of Engineering at the City University of New York, USA. Prior to that, he had held faculty and visiting positions at the universities in USA, Canada, and India. He has also worked as telecom software engineer and control systems engineer in industries. He obtained his PhD in computer science from the University of British Columbia and BS and MS degrees in electronics engineering and system automation fields from the Indian Institute of Science. His areas of research includes autonomous networked systems of things and SDN for fault resilient operations. Over to you, Professor.
Okay, thank you. Yeah. Good evening, everyone. It's a pleasure to be here. I keep visiting IASC quite often. As I mentioned, earlier, I've been an IASC alumnus for many years ago. But I keep coming every year, and we participate in conference events and other things. So it's like getting back to my own mother place kind of thing, in some way. Anyway, this talk is about modeling paradigms and tools for autonomy management in complex network systems. Everything is based on models. I'm going to focus on what's called the cyber physical systems. Half of them are physical things, and half of them are software in some way. The basic software is, we humans have to write it, at the end of the day, and the physical world is not intelligent, like wheels in a car, roads, they are not intelligent by themselves. So the software is made intelligent to make the collective system look intelligent. I mean, that's what it is. When you look at robots, it navigates on the roads and things like that. The roads are not, they're just brick and mortar, but the software is made intelligent. And how we going to improve the intelligence making capability with this model? It's all based on models. Okay, that's the whole thing. Again, I have a lot of slides, but I'll skip a lot actually. Just again, the slides are available for details here. It's always, the devil is in the details. But we don't need to talk all the details here. So you can kind of read that. The focus here is about self-managing systems. The systems manage themselves. Okay, and the software helps them manage it. Okay, but humans actually develop that self-managing software. Okay, and this is about every system runs algorithms. Okay, now the algorithms have to be verified correctly, and then you have to assess the algorithm. There is a subtle difference between the verification and assessment. Verification is about whether you're doing the job right. Okay. Assessment is about how good you do the job. It's like, if you're a student, the verification is that you'll pass the course. Now I'll get a C grade, I'll still pass the course. I meet the functional requirement. It's not about getting a C grade, it's about how good you do in the class. Whether you get a grade, whether you get a B+, whether you get a A-. It's not about just passing the course. Okay? So verification is about getting at least C grade. That's the verification part. Assessment is about how good you get a grade, how often you get a grade, what's the probability, those kind of things there. And that's the world we are in today. So there's a lot of software engineering aspects built into it. So I'm not going to read everything. There is a thing called a model checker tools that we believe will make the design of systems much easier. We are all about talking about models. I mean, without models, none of the systems will work. Like, when I talk to someone, I don't know what that person is thinking. Suppose I'm talking to John, I don't know what exactly John thinks, but I can make a mathematical representation of John in my mind, and I'm talking to that mathematical model. And then I refine that model. So modeling is a part of our life. The question is how flexible you can do the modeling, how you can softwareize the model development effort. Okay. That's the idea here. We are talking about models. Suppose I'm talking to John, I want to find out what his utility function is. So I give him some $100 and see how much he smiles. Based on the smile, I know that this person wants dollars. So based on how much he smiles, I give him more dollars or get back some dollars. That's like an economic function, right? I don't want to I want to keep him happy, but I don't want to give too much money. Okay. Suppose I give the $100 to Bill Gates. Obviously, he will not go to smile because he has seen billions of $100. So I had to use a different utility function for that. So that's like an example of a model. Okay. So again, there is a number of case studies we developed at CUNY. One is supply chain management networks. It's all about resilience. Resilience is not about doing things, it's about how you fight back when bad things happen. It's all about that. Artificial intelligence is about, it's not just doing things, it's about how you fight back bad things. Okay, and that's what this thing is about here. So what is this one here? How complex is the handling of complexity? Of course, we all deal with complex systems. If the system is simple, I don't need a an AI tool. The systems are complex. And how complex is the handling of complexity? Okay. The other thing is faults are going to occur. Faults means there's something that's unexpected. Suppose I fall sick. There's nothing you can do about it. I had to recover from that. So the question is, I had to proactively plan to recover from that. Okay. The question is whether I'm a pessimist or not, because I always carry some aspirin tablets. Just in case, there is a dizziness that comes, I'll take some tablets. So it's not that I need an aspirin every day. So in that sense, I may become a pessimist. Maybe it happens once in 10 years, once in a year. So I don't know when that's going to happen. So sometimes you balance between pessimistic and optimistic approaches. Okay. Sometimes if you are an over pessimist, you stop enjoying life. You worry about tomorrow and then you forget the enjoyment of today. On the other hand, if you are an over optimist, then you get stuck into some unknown situations and then you're not able to recover. So you have to have a balanced optimism and pessimism. And the same thing goes with the algorithm developments. When you develop algorithms, the algorithms are designed to deal with faults. Okay. If the world is fault-free, there's nothing, there's no need for you. Right? Computer scientists and engineers are needed because something faults happen. Okay. And you have to be able to deal with those faults. And this has been there going for a long time. The question is how good you deal with those faults and how you fight back and how you improve your fighting back capability. I lose the battle today, but tomorrow I'm going to win. How do I reconfigure myself? And this has to be done automatically. Okay. So that's the kind of thing there. So this is an example of a case study that we do for General Motors. I'm not going to read all the things there. You can see that this is an example of a complex system. You have multiple autonomous cars. There is no driver. And I don't know whether this is going to, when it will come to India, I don't know that. But in a futuristic highway, that's what it is. You have cars, and you have a built-in cruise control system, and you have a road hazard, like an obstacle thing there. Now, how does the cars move? Okay, yeah, there's no driver there. If you look at the human driving, the human is very intelligent, but he's terribly slow. Okay, whereas here, if the green car tries to move to the left, there's already a brown car, it will cause a collision. Okay, obviously, we all know that. When we change, you just look at the left side, right side. So we all do that. Now, how do you make the cars do this? Okay, and the software that does this control, because the car, when there's no driver, there is no human intelligence there. It's all about wheels, tires, and the road friction, road wetness, all sorts of things are there. The control software probably runs in a cloud, which is based in a data center in Australia, for example. It's like, so right now my brain is inside when I drive. Imagine that my brain is outsourced to Australia. Yes, it's a science fiction kind of thing. I ship my brain to Australia, and you have the internet, which acts like a nervous lines that connects to my physical body. My legs and hands are here, physically here. But my brain is in Australia, right? Now, the brain thinks. Now, the data center thinks. It collects the data from the cars, the speed positions, and then sends back the control signals to the cars, and all have to be done in real time. You have only like a 50 milliseconds left. You see, so there's a lot of engineering challenges there. So that's one example here. The other one is we use what's called a UAV-based cyber fencing. Multiple UAVs try to look for a bad event. Something, somebody is trying to create an intrusion or whatever it is. Okay? We call this a cyber fence. It's a kind of just like a physical metal fence. This is based on UAVs that we call this a cyber fence. So we look for any suspicious events that are happening, where somebody is driving extremely fast. Maybe that person is in a hurry, or that person has some malicious intent. Okay, so those things will be, the data will be collected by the UAVs and then reported to the control center and for a follow-up action. Okay. The other one is a supply chain system here. We all know, we go and do some shopping and things like that. Now, how do you make sure that the products are available on time? And particularly with today's geopolitical conflicts, we all know the issues, right? So something happens somewhere, and the world is connected, and then it has an impact on how we live. And how the AI system can proactively model these faults and get ready to do these things. So this is an example of another system. It's a fault resilience. It's not about supply chain network. It's how you recover from faults. And even before you deploy the system, I'm going to measure your ability to fight back. You're not deployed yet. But even before deployment, I have to measure the ability to fight back. And how do you measure the ability? Because unless I drive a car, how do I know that I'll be able to, how do I get a license? Something like that, okay? So it's all about modeling. You have a mathematical model of the system, and then there is a AI runs on that mathematical model. And this is how it's done. It's not our idea itself, that's the way AI is done. Our contribution is about a special approach called probabilistic model checking. How it can improve the modeling capabilities. And how I can adjust my thinking process. It's all about that. Everyone is intelligent. It's about how you manage your intelligence. Some people recover quickly. Some people recover after some time. Eventually they recover. The question is real-time constraints, all those things. And how do you measure the resilience even before the system is deployed? This is very important. Suppose I have an autonomous car. I had to specify the skid resistance. Okay, if there is a water puddle on the road, a wet road, the car will be skid-free with a 99.99% guarantee. Otherwise, I won't buy the car. So, of course, personally, I always drive a manual car. It's all, I preach autonomy, everything in the class. But when it comes to me, I'm happy with a manual driven car, so I have more control over it. But that's a separate issue. I tell my son, he's a doctor, medical doctor. He says, no, if everyone is healthy, you don't have a job. Somebody has to be sick so that you have a job. And he gets angry with me. Anyway, that's a separate story here. Sorry. Okay. Now, now the part here. So you have a system which is made up of core algorithms. It's like hands, legs, ears, eyes. These are the core parts of our functioning. The eyes don't think. Eyes only sees what is there. And the brain is the one that thinks. Your legs are the ones that allowed you to walk, but the control comes from the brain. Okay. So you have a model of that here. Okay. Now, here is the thing there. How do you measure the resilience? A student gets a A grade, a student gets a B grade, a student gets a B plus grade. How do we decide that, right? Assuming that they're all intelligent. The question is, no, they didn't answer certain questions correctly. Okay. It doesn't mean that they are bad. Okay. So, it's about, so let me show this one here. Okay. So what this means is that there's going to be faults. You cannot imagine, you cannot have a fault-free world. The question is, how do you react to faults? And how do you react how do you measure your reacting capability, your fighting capability? Suddenly I fall sick, I fight against it. It's like a defender versus attacker kind of thing. Somebody wants to make me sick, okay? But I don't give up, I just fight back. Now your question is, how do you measure that fight back capability? Okay. Some people, I had to take the medications on time, I had to go to the right doctors, that's the kind of thing there. So maybe the doctor is expensive. Maybe to cut the cost, I may to go to some specialty where the cost is cheaper, but in that process, my recovery is slower. So it means that there's nothing wrong with the doctor, this is wrong with my algorithm. Okay, I traded off the dollars for the specialty of the doctor whom I go. So these are all part of the algorithms. So how do you measure that ability? Okay. So you can see that we plot the hostility of the environment, how bad the environment is, like a COVID pandemic times. Things were bad, but still you recovered. Now, how do you measure the recovery capability, recovery resilience? Like back in the US, 9/11 happened. Many of you may not be small children at the time, but it bounced back. Okay, as a society, how you fight back. So this is about how you fight back. So the more the hostile things are there, you're going to lose something. Suppose I slip and fall down. I'm not going to just fall down. I had to get up. Maybe I just broke my leg. I twisted my ankle. But I still walk. Okay. Maybe I should not have stepped on that slippery road. That's my fault, but the accident has happened, so I fight back. And how you measure the ability to fight back, this is important, okay? So that you don't make that mistake again, okay? So that when you have this kind of ability in this AI system, you develop more trust on the AI system. You buy an autonomous car, because there's no driver there. So you want to make sure that the car will not skid when there is a slippery road, or the car will slow down when there is moisture on the road. Okay. So all those kind of things, you have to develop a confidence before you buy an autonomous car, right? So how do you develop that number, 99.99% safe? It's not just put a number there. It has to be measured. Like I visited General Motors lab a few years ago. They have a lab. It's where they sprinkle water on the road tract. It's not a public road. It's a private road. It's a lab where they sprinkle water on the road, on the test tracks, and they drive cars. And then the car skids and then gets in an accident, nobody gets hurt because it's only a lab. So that's an example. Then you improve the algorithms so that you quantify the skid resistance. So the cars adapt. Now the question is, how do you quantify the quality of adaptation? How good you adapt? That's the question there. If we all adapt, we have to survive. The question is, how do we quantify what's the quality of adaptation, and how do we quantify that quality of adaptation? And that's what everyone is different, because everyone runs a different algorithm. Maybe they're money-minded, money-conscious, or they didn't have the resources, whatever it is. So that's what we are trying to do in the software systems. Okay. Okay. So there is an adaptation logic, and the adaptation logic tries to improve. I cannot change my legs. I cannot change my hands. That's God-given. But my brain can control how I use my hands, when to use the hands, how much force I had to apply to lift an item. And that intelligence comes from the brain. How do you restructure the brain? We all constantly think. And we have a mathematical representation that runs in our mind, so we could become better persons to deal with the situations in the future. Okay. So that's the kind of thing there. So this is about the quality of adaptation. Now you can see that this system is more resilient. Because even in very toughest situations, it's able to do better job compared to the blue system there. The blue system does good when everything is nice. Because the hostility is low. When everything is nice, I'm good. But something goes bad, my performance is worse than a person who behaved less than me when things were nice, but that person continues to behave good, even in the worst case scenarios. So it's about worst case scenarios, okay? Because you don't know what's going to happen in the road. Right? And that's what the thing is. So we try to measure the quality of resilience. So resilience is a qualitative term, but how to quantify the resilience? Suppose you get low points in the exam, you recover. So maybe you didn't focus on certain subjects. Maybe you change your style of studying, all those things. And we all do that, right? See, nobody has to teach that. The question is, when you do it in the software, how do you quantify that resilience? So that is the thing here. You can see that this is an architecture of a system. The infrastructure is about the physical thing there, like legs, hands thing there. Then you have an algorithm that runs, okay? And and the interface is the one that the outside world sees, okay? So you see how much I smile. I mean, you don't know what's happening in my mind. That's my interface, because I want to give a nice picture to the outside world. Even though I have a lot of difficulties, I don't want to tell all the difficulties to everyone, right? But I have an algorithm to deal with those difficulties, but I keep a smiling face outside. And if there is a bad thing happens, I adapt. That's the idea here. And the external assessment module assesses how good you adapt. So that's a kind of outside person. It's like you're writing an exam, the instructor evaluates it. The instructor is basically an outside person. The person assesses how good you respond to certain scenarios. Okay, so sorry. I'm sorry. I should. I'll just turn it off. My wife is calling from US. Yeah, I'll just. Okay. Again, the assessment module, that's the one that we are focusing here. Okay, and the assessment module will adjust these algorithms, do things differently. I cannot change the infrastructure, but I can change the way I manage the infrastructure. Okay, and we all do that in our day-to-day life. And how do we automate that process? And the model checkers, everything comes in that external assessment model. So I have a third-party assessor that tries to figure out how good I am, and it tries to give me instructions as to how can I improve that. Okay. A system that's good, but it's not verifiably good, is not good enough. I'm good, but that's only in my mind. I had to convince you that I'm good. Okay. Now, Bill Gates, I'm sure you know that, he doesn't have a college degree. He dropped out. Of course, no, Bill Gates is. But if you go for a job, you have a degree, and Bill Gates go for a job, who will get the job? If a person goes strictly by the thing there, because the university has given you a certification as to your 3.8 GPA, for 3.9 GPA, whereas Bill Gates, even though he's good, he doesn't have a certification. So the university is like a certifier. It certifies that you're good. And the employer hires you based on that certification. Because the employer develops a trust in the certification process so that the employer assumes that you're good. Of course, you prove your worth after getting into the job and other things, but at the time of hiring, it's something like that. We assign 3-star rating, 4-star rating. It's about that. In contrast, auditing is about what went bad. A doctor is an auditor. So you fall sick and you're not recovering as much as you should have. You're taking the medications, all those things. But doctor is not a god. He helps you to recover. So when you're not recovering as much you should have, the doctor audits your profile. Maybe what type of medications you're taking. Maybe I should change the thing there. Maybe the doctor missed something in the previous analysis. So he does an auditing and then tries to improve the recovery process. Okay, that's like an auditing process there. Okay, now here is the thing there. Uncertainties are going to be there. We deal with uncertainties. Okay, so how do you deal with uncertainties? It's about how you're prepared for dealing with uncertainties. So the external environment, hostile events, is divided into 4 subsets. The set of things that I know. Okay. It's not about knowing, it's about what you know that you know. I know computer science. And I know that I know computer science. This is important. Otherwise, you have to be able to know what you know. Then the set of parameters that I do not know now. They are called knowable unknowns. I don't know now. But if I get the resources, I will come to know about it. I don't know biology myself. But if I had to, if there's a scenario, of course, it's too late for me to study, of course. So I can take a class in biology and come to know the subject that I didn't know, but now I come to know. Okay. Then the set of things that I know that there are known impossibilities. There are certain things I will never come to know, so I keep away from it. So you have to have the intelligence to keep away from things that you can never master. Okay, and we face that. And the 4th one is what's called unknown unknowns. The things that I don't know that I don't know. Okay. If I know that I don't know, I'll either keep away from it, or I try to learn to know the unknowns now. Right now I don't know, but I know that I have the resources to know the unknowns, or it's too much difficult now, I'll just keep away from it. And the world is made up of like that. Okay. So this is stated by Don Rumsfeld, the defense secretary, during a NATO meeting 25 years ago, in the post 9/11. The US has a strong military force, but how come they are not as successful as they should have been in dealing with the terrorist events? And he said that I cannot think, I cannot know what they're thinking, what the terrorists think. And I don't even know what I don't know. So even if you have the strongest military, you still lose. So that is, and that's true for today's scenarios there. Okay. The thing is that there are going to be, if we have a car, autonomous car, why can't they have 100% skid resistance? Can the automobile manufacturer say this car is 100% skid resistant against wet roads? Can he say that? Can I say 100% resistance? Why not? It's probabilistic. There may be a 1 in a million chance that the car may skid. So it's definitely less than 100%. If I say 100% I'm good, that means I'm totally wrong. I can say I'm 99.9% good. I'm 99.5% good. 95% good. I have to give a number, but it can never be 100%. And that's true for anything. Right? So that's what's the thing there. Now here is where the modeling paradigms come into play here. You have a network system which are made up of algorithms, components, everything there. And you have a model of the system, phi, yes. As I said, no, when I talk to you, I'm talking with a mathematical model. Suppose your name is John. I have a phi of John, which is a mathematical representation of what you want, what makes you happy, what you don't like. So all those things are in my mind. Maybe I'm wrong, because I'm not you. I cannot think what you're thinking, right? I can only have a mathematical approximation of what you might be thinking. And that's true with anyone, friends, everyone, right? So the question is, which is the modeling paradigm that they use? One is called an operational paradigm, operation models. This is about deriving some mathematical equations. So intelligent systems have been around for a long time. So it's all about modeling, okay? Like for example, you assume a Poisson model of network traffic. That's an approximation. The real world traffic is not Poissonian, but you make an assumption that it's Poissonian because you can mathematically solve it. Otherwise, no, you spend a lot of time in solving a problem, and you spend the time in solving a problem that you can better do it with a simple approximation. We all do simple approximations. Okay, it's quick and shorthand, but there is more accuracy there. The other one is I build a a close to real software prototype to mimic its runtime behavior. Suppose I want to build a car, okay? I build a toy car. Like a toy car is like a 2 feet by 2 feet, okay? And I can run it on the track here, and I can make it skid, I can make it, because it obeys the laws of physics. Whether it's a big car or small car, it obeys the laws of physics. I can apply all these control mechanisms, study those mechanisms. If I make a mistake, there's nothing damage done. Because there's only a toy car, it crashes against things there, nobody gets hurt. Okay. Then I can apply that knowledge to the real world. So it's like a, but it takes a long time to develop. The third middle ground, this is our conjecture. It's called a model checking systems, where you can achieve reasonable accuracy. At the same time, you can develop the software in quicker time. Because if you want to develop a software prototype, the prototype takes 2 years to develop. Say, I want to build a car. In order to build a good car, safe car, I had spent 2 years to build a toy car, test it thoroughly, do all the lab setups, everything, and then build the real car. So the 2 years of development time is a lot of time, right? So that's the kind of an example there. Whereas model checker offers a middle ground, it has a reasonable accuracy of prediction. It can change the things in the software dynamically, so that you can change your profile. It's like, I am Ravi, I become Ravi prime. I change my algorithm. I become Ravi double prime, another algorithm. But I'm just one here. It's all about software. You have different models and then figure out which Ravi prime or Ravi double prime will work better in this scenario, and then you become that person. I cannot change my laws of physics, my physics, but I can change the way I think. And we all do that, right? We put ourselves in different frameworks and then see how we'll behave in this way, how we'll behave in this way. It's all in your mind. And we humans are doing that. You don't need a computer to do that. We have been doing that, right? The question is, with the AI systems, how do we flexibly compose different algorithms, different methods? It's all, because that's not really deployed. It's all about the software, and you can test it out before you actually deploy the system. And that's where the development becomes easier and more provable. It's about provable guarantee. Suppose I guarantee you something. I guarantee you that you'll have achieved this goal. See, that guarantee has to be provable. I can guarantee anything you want, right? But how do you prove that guarantee? How do you guarantee that guarantee? You see? And to guarantee that guarantee, you need a software tools that runs in the background and then does a lot of expensive testing, and so that you stand by those numbers. Okay? So that your systems are better in that way. Okay. It's like, so my wife works in a pharmaceutical industry. She just retired. They do what's called a clinical testing. Suppose a new disease comes, like a COVID-19. The COVID-19 is an extreme example, but there's a new disease. So the pharmaceutical industry comes the new drug. But I need to test the drug before I can sell it to the consumers, right? Which means I need a sick person. How do you test a drug? So suppose I say that, no, okay, you're doing very healthy. Can you get sick so that I want to test my drug? Will you do that? No, right? No, right? Nobody wants to get sick because I want to make money as a pharmaceutical company, right? So they do what's called a clinical testing. Clinical trial means we administer, not me, the pharmaceutical companies administer small dosages of disease-causing virus to the humans. So the humans get symptoms of that disease at a very low level, and these are all regulated. And then you test your drug on that diseased patient, and then see how the patient reacts. In order to get the patient to agree to get sick, the company pays an honorarium, like $5,000, $10,000. Okay, I'll give you $10,000, so you please get sick. Natural sickness is okay. But you want to get sick so that I can test my drug on you so that I can make the money. Right? That doesn't sound right, right? So I'll give you $5,000 so that you kind of volunteer to become sick. And I test my drugs on that. It's a kind of thing that. It's all about models, actually. So eventually I need a thing to test. Okay. There is a metaphorical statement by Professor Julia Pearl, who is a well-known person in game theory. The best model, suppose you want to develop a robot system to manage a cat. Like about time the cat gets hungry, how do you feed it, and all those things. And it's a robot, right? It doesn't know it doesn't know the operational semantics of a cat. So you have to have a model of that cat implanted in the robot so that the robot can feed the cat on time. The other person who is going on a travel, the cat is at home, the robot has to feed it, right? So how do you develop that cat, that model? So he said that the best model of a cat is the cat itself. In order to train, develop a model of you, I had to become you. So it's like a cloning. So you don't want another clone, right? So that's a kind of a metaphorical way of doing this. So there is a thing called, we all make inaccuracies, make inaccurate decisions. So what's the gold standard for inaccuracies? We're going to make mistakes. Every one of us. We think of something, and then when we find that the output is different from what I thought it will be, then we correct it. And that's what the human intelligence is about. There's nothing like in a single shot, you make always the correct decisions. There's nothing like that. There are unknowns, uncertainties. So that is the question is how much mistakes you make. And what's the gold standard means there's a reference benchmark as to how much mistakes you can afford to make. Making mistake is not a mistake. You see, making mistakes is not a mistake. The question is, how do you recover from those mistakes? And how do you measure your recovery capability from mistakes? And what's the gold standard? Gold standard, what's the benchmark to measure your ability to recover from mistakes? And that's what the whole thing is about. You can see this is the kind of an architecture. So you have algorithm processes here, okay, and you have environment modules. The environment modules basically is supposed to inject fault events. I want to test how you recover. Okay, so I inject a bad event called I'm going to make you forget on something. I mean, you forget means you see a problem, right? But imagine that in a model, I make you forget something and see how you recover. Okay, so this is the model checking facility here, and the application interface is the one that you evaluate how good you recovered. Okay. So there are two things. One is what's called a safety. Safety means I should always behave correctly. Basic functions, like a car should reach on time to a destination. Suppose I'm going to the airport, so I have to reach the airport. So the driver will get me that. But if the driver gets me there after 8 hours, that's not, he met these functional requirements. He said, I will get you to the airport in a finite time. But that's of no use, you miss the flight, right? The question is how good the driver meets the requirement. So that's the assessment part here. Okay, that's not a liveness. How good things eventually happens here. Okay. So this is again, I'll skip it here. So this an Uber taxi driver, the multiple things here. The question is evaluate the on-time passenger drop-off. The comfort and other things, the comfort ride and all those things are there. The on-time drop-off. So that's what you evaluate. And how do you evaluate? You evaluate with a mathematical model and then see if I do this, when will it drop? So you add some cushion to it. Maybe I need 45 minutes to get there. Maybe I'll book the taxi an hour and a half before. So you need that 45-minute cushion, right? How do you decide that 45-minute cushion? Based on a mathematical model, right? Because you want to leave some room for margin, right? So those kind of things there. So here is the system that observes. It observes your capability. I know you're capable. And I'm observing your capability, I'm trying to measure the capability. How do I do that? So the capability is God given to you. Your intelligence is God given, right? I just only observe. So I inject some test events, okay? See how you react. And then based on this finite set of measurements, I evaluate your capability. Maybe my evaluation is wrong. Maybe the instructor gives you B grade where you deserve A grade. The instructor made a mistake. You didn't make a mistake, but unfortunately, the instructor grade is it kind of stands for a while. Of course, the students have a way to challenge that, but sometimes the instructors are also not gods, right? So sometimes they make a bad assessment. So this observer is the one that assesses the various capabilities of that system under test here. So you inject artificial faults. This is important. Okay. I don't know how do you test. It's like an exam question. Yeah. So the exam testing is like you inject fault events and then test how you react to it. Okay. So this is a view of how the algorithms work. It's all different algorithms are there. So you have the environment, the bad things. Somebody from outside gives me bad events, like there is an infectious disease, there is a heavy snowstorm. So all those things happen. Okay. We have to react to it. You cannot go and control it. You can only react to it. There are two algorithms, P and P prime. Now P works correctly with the environment condition E1. It also works correctly with the environment condition E2, but does not work correctly when the environment condition becomes E3. If I fall feverish, I'm still able to answer the exam question. Maybe 100 degrees, maybe 102, it's in Fahrenheit, not in centigrade. 102 degrees, maybe still okay. But if I fall 104 degrees, then I fail. Is something like that. Whereas algorithm P prime fails with the E2. So we say P prime is less resilient than P. So what do? You switch from P prime to P. P prime is less expensive. Normal type. So the thing is, there's a 90-10% rule. 90% of the situations that happen, or bad things that happen only 10% of the time. It's like a rainfall, and it doesn't, maybe rainfall is not a good example. Suppose I slip and fall down. It's not that I slip and fall down every minute. Maybe once in a month I slip and fall down. But I worry about those things every day. What happens if I slip and fall down? What happens now? In that process, I spend more time, more resources in worrying about things that happen only once in a month or maybe once in 2 months. So obviously, I want to spend less resources. Okay, what happens? If I slip and I'll worry about it at that time. I don't want to worry about it now. That way, I can spend the time in useful things rather than worrying about an event that happens once in a month or once in 2 months. But if I fall down and break my leg, then I go back and maybe I should have been careful, but it's too late, right? And we all go through that process in some way, right? We blame the past, but nothing can be done. And so these model mechanisms make you a better person, so make you make better decisions. You cannot be 100% correct, but maybe you make better decisions. That's the kind of thing there. So again, I'm going to skip some of the details here. Promila is a software language that is only 10 minutes, maybe. Is that correct? 10 minutes, I think? Okay, I'll try to skip many of these things here. Promila is a language developed at Bell Labs in the 90s. So these mechanisms have been around for 30 years. The question is, they are refurbished, rechanged. Though when the languages were defined, they were worried about only the correctness part, whether the algorithms work correctly or not. Today, we are in a situation where the correctness is taken for granted. The question is about how good you do. Okay? It's not about just passing the course. It's about how well I pass the course. Whether I get a grade, A plus grade, B plus. I'm not satisfied with C. That's the world we are in. There are many languages. So you develop a discrete event simulation. So what happens tomorrow? Suppose I want to plan for 2 weeks. What happens to tomorrow? I'll go to a restaurant here. I'm going to meet my friend. I'm still today. Okay. I'm going to do, so all this, put the events in your mind. Okay. Then what happens the day after? Tuesday, He said today, tomorrow is Tuesday, right? Wednesday. Again, you go through the events based on what might happen tomorrow. I'm still today, Monday. So you plan for a week. It's all discrete event simulation. And then you work a style, and then say, okay, if I go through this sequence of events, I will succeed the goal in 8 days. But you're still on Monday. The 8 days already happened. When I go to tomorrow, things might have changed. Maybe your friend fell sick, he didn't show up for the meeting. So you had to rearrange everything. Then you have to rework out the thing there. Okay. And this makes it easier. These model checkers allow you to execute these alternate combinations and configurations with the data centers available, extreme computing available, GPU computing available. You can ship the model checkers to execute in these things there. So this is possible today. It was not possible 15 years ago because this model checking was expensive in computations. So now with the data centers, with the parallel GPUs and available, you can reinvigorate these model checkers to run extremely fast in real time. So that's the premise here. Of course, the PhD research is all premises, right? Things were not possible 10, 15 years ago. Now they are possible. It's only still a premise and a conjecture. And we are trying to do it in the lab to improve things here. This is an example of your stored supply chain, how you model. See, regardless of physical system, the software is just a computer. It's just to execute instructions. So how do you model a physical system? See, in this case, the truck gets into an accident, let's say, which means the supply shelf becomes empty. The item that are to replenish the stores, they didn't show up. So the customers find an out of stock scenarios. It's like a gas today, right? Well, gas is not out of stock, but the price has gone up. Imagine that something goes bad. Okay. So how do you model that? The languages allow you to model them. So if you look at, so how do you simulate an accident in the computer? The computer doesn't know what an accident means. The operational semantics of an accident, the computer is just a software. Okay. So there's a thing called, the language has many constructs that allow you to simulate accidents, simulate road frictions. Okay. See, it's kind of hard to think that way, but imagine, let me use this example. Suppose your car is driven on the road. Now the tire, how does the car go skid free? The tire, there is a friction coefficient on the road, and the tire tries to make a right. Suppose you trying to make a left turn. The centrifugal forces try to make the car go to the right, but the tire friction, the road friction holds the car, and the driver knows how much turn he has to do so that he can avoid if you do it fast, then the car will skid, right? Now, how do you model this? Now, at the mathematical level, at the programming level, the tire is a computer process. It's a computer program. You model this as a computer program. It's not a computer program. You model this as a computer program. And the road is a computer program. And this sends a message to each other. In other words, the tire talks to the road. Okay, tire says to the road, okay, I'm going to beat you by going through it. Now the road tells the tire saying that I'm going to make you skid. Now let's see who wins. The tire is talking to the road. It's basically a defender versus offender. The road's job is to make you fall down. And your job is to hold from falling down. And the tire and the road talk to each other by sending messages. And here, there is a random leak in the channel. And the random leak means it's a randomly leaks. Sometimes, 90% of the times you succeed. 10% of the times you fail. Okay. The road wins. 90% of the time, tire wins. 10% of the times, the road wins. And those things are modeled by leaking the messages. I send a message, but the message gets lost, kind of thing. Okay. So this is a kind of an example there. So again, there are too much details. Yeah. Just to skip through this one here. So again, let me. It's all about state transition analysis. I'm sure you have a course on software engineering that does state machine analysis. So it's a Markov decisions and things like that. So let me skip that here. Now, this is the case study. Again, I don't think we'll be able to go through it very detail. This is a case study we're developing using model checkers. Okay. It's about surveillance system. You have a battle terrain, okay, and these are unmanned vehicles. They look for hostile objects, okay, where there's no humans are there. This is basically a drone looking at the objects in the sky. It's like, you put a set of drones over Bangalore and see is there any suspicious object flying, okay. This is called a cyber fence there, okay. Now there are birds flying, obviously. There are planes flying. Now, the fuzziness is about sometimes I look at the bird and then, oh, I thought I saw a plane. I looked at it for 1 second. I thought I saw a plane. Sometimes you saw a plane, but you think, oh, no, it's a big eagle. I don't think it's a plane, right? So there's no bad intent in that. There's no bad intent. Just I was careless. I quickly looked at it. I'm not going to look at the bird for 10 minutes. I'm going to look at it for like 1/10 of a second and then say, oh, there's a bird or a plane, kind of thing there. Now, a malicious guy knows it's a plane, but he says, no, I saw a bird. It's an enemy plane, but I saw a bird. Why? The malicious person's intent is to let the enemy plane slip through and cause damage. Right? So it's like a fake news, A person who implants a fake news knows it's a fake news. Okay, the ground truth is known, and then that person implants a fake news. Now, innocent bystanders think it's a genuine news and then pass it around. Because on the surface it looks like a genuine news. I kind of pass it around. Oh, I saw this news. Okay, you spread it around. Actually, I'm doing a bad job being a good guy. I'm being exploited by a bad guy. And by the time I find that it's a fake news, it's too late. I already spread out, right? That's the kind of thing there. Okay. Again, there's a lot of details here. We develop robotic simulators in the lab, ROS, Gazebo, and again, we have some papers. If you're interested, I can send you the papers. But the general idea I get, right? There are drones, but some of them are malicious. But you don't know who are malicious, right? So that's the problem there. The malicious entity camouflages as a good entity, okay? So we study those problems with the model checkers, okay? These are all real complex systems, okay? So I'm going to skip this one here. So we do, again, and I'll not be able to go through already. Can it take another 7-8 minutes? Okay, just let me finish it off to the extent possible. We do what's called a replica voting. Redundancy is always part of our life. Okay. So, and this replica is malicious. It falsifies the result. Okay. And do what's called a majority voting. I don't know the ground truth. Suppose you say the outside there is a heavy snowfall. I don't know. I've not seen the outside here. Somebody says that. How do I know if there is a rainfall? Snowfall. I know that in Bangalore there may not be rainfall, but suppose I don't know that. So maybe there is a snowfall there, but for that I had to go outside and look at it. Then how do I find out the truth? One person said there is a snowfall. Then I asked the second person, did you see the snowfall? That person says something. And then I asked the third person, did you see the snowfall? I asked 10 people and then take a majority, how many people say yes and how many people say no. And I make a kind of a decision. Okay. That's the kind of analogy here. It's like reading multiple newspapers. Suppose I read a newspaper, there is a news item there. Maybe it is not true. So what do? I read a different newspaper about the same news item. Okay. Or you go to a doctor, and the doctor says, I have a blocked artery, so I have to do a surgery immediately. Okay. Now I start doubting in my mind. Symptoms are okay, kind of thing, but the doctor says I have blocked artery, I have to go for surgery. I start doubting, maybe this doctor tries to make money out of me. So what do? Sorry? Go to another doctor. Now that doctor says, no, you're perfect, you're fine. So now what do? Okay, the second doctor tells me what I want to hear. Now, can I stop at that point? Yes or no? No, why not? Because the second doctor told me what I want to hear. Why can't I stop at the second doctor itself? Maybe the first doctor was right. The second doctor was wrong. You see the point here? See, the body is mine, but the analysis is by the doctors. The doctor looks at the various symptoms, ECG results, the blood, cholesterol levels, all those things. Maybe the first doctor was right and the second doctor was wrong, and I want to live. So I go to the third doctor. Now, how many doctors I go to? Okay, and depends upon, every doctor I go, I have to pay consulting fees. So there's a cost constraint there. If it's a simple leg pain, okay, what if the doctor gives me a wrong medication? Still it's okay. But if it's a hot leg scenario, I have to be careful, right? So more doctors I consult, then I do a voting. Okay, what this doctor said, what this doctor said. That's a data science problem. Okay. So this is an example where there are multiple radars. One radar is malicious. There's an enemy plane flying. Two of the radars say that they detected a plane. The malicious radar knows it's a plane, but it says I did not detect a plane. Okay. And the voting apparatus is just a counter. It counts the votes. It doesn't know what a plane means. Okay. So out of the three, two of them said there's a plane. One of them said no plane. So majority is that the plane is detected, and it sends the information to the command control unit, and the command control unit dispatches a missile to destroy the plane. Okay. Now, if this was a wrong decision, maybe inadvertently trigger what? There was no enemy plane. So just a scenario, suppose there was no enemy plane, but the system thought there is an enemy plane. Maybe there was a bird flying, big bird flying, but you thought it's a plane, and you triggered a missile. So what happens? You may trigger an inadvertent war. Everything was peaceful, but it's destroying a plane, you start a war. That should not have been there in the first place. You see the point here? So there is a lot of things are there. These conditions can be evaluated around time here. Again, let me try to skip it here. So it's just a simple example here. So the question about what is 2 plus 3. We all know it's 5. But I don't know the answer to 5. Because I'm just learning how to add. Okay. So it asks the question, now one of them says that the 2 plus 3 is 26. Deliberately. Okay. The other guy is 2 plus 3 is 5, but they take more time to compute. See, telling a lie is easier, quick. Telling a truth takes time, because I had to compute the truth. Okay, it takes time. Okay. Now you ask for a vote. Okay. And then you get to, I assume that the one bad guy, and the FA is the number of real bad guys. So I need 2 yes votes. 5 guys are there. I need 2 yes votes. If I to get 2 yes votes, that means at least one of them is a good guy, and the good guy never tells a lie. And that's good enough for me. If I ask a question, there are 100 students in the class, I don't want to wait for 51 responses. Maybe I assume that there are 10 students who may not give the correct answer. So I need 11 responses out of 100 students. If they agree, that means there is at least one good guy who responded, and the good guy always gives the correct answer. That's the intuition. Here is the key there. The bad guy does not behave bad all the time. He behaves badly 1 in 10 days, 9 days he behaves correctly. If I'm a pickpocket, I don't do a pickpocket every day. What happens if I do that? One day I'll get caught. I don't want to get caught, but I want to keep doing this. So one day I behave good, 9 days, one day I pickpocket, 9 days I behave good. So that's so the probability of my bad behavior is 0.1, whereas a good guy always never pickpockets, right? So that's the intuition here. Sorry. Okay, so this is the intention here. Finally, now they do a voting. It takes a while to compare the votes actually, and then you deliver the result 5 here. So let me skip all these things here. Now there are two bad guys. See, this is important here. There are two bad guys, but I thought there is one bad guy there. I made a wrong assumption. But I don't know who is bad. There's nothing written in the foreword that I'm bad, you see, right? It's all about my intentions, what I do, right? On the surface, I look good. I camouflage myself as a good guy, when in fact my intentions are bad. But I'm not going to expose my intentions outside the world, right? So there are two bad guys, but the algorithm thinks there is one bad guy, at most one bad guy. Okay. Now what happens here? Again, the same question, what is 2 plus 3? Now the good guy, the bad guy, one guy says R is equal to 26, 2 plus 3 is 26. The other bad guy says that R plus 2 plus 3 is 49. Both are wrong. Okay. The good guys keep computing for a while and then come up with the correct result. Now when the voting takes place, now these two guys collude with each other. It's like saying, I'm going to give an answer. You just vote for me. I'm going to give a wrong answer. I kind of do a back channel communication. I'm going to give a falsified answer, and can you vote for me? But people won't see it, that back channel communication. Okay. Now these two guys, they know that is wrong. Okay. But this guy says yes, 26 and 49, they are the same. So finally it's a vote. Vote is based on whether the proposed data matches with what I think is the correct data. So when you say the outside is snowfall, in my mind I know what the status is, and when you say, I compare with what you say with what I think outside is there, and if they match, then I say yes. If they don't match, then I say no, right? That's how you vote, right? So now what happens here? You deliver 26 as the correct result. That's an undetectable incorrect response. Now here is the algorithm correct. Yes, exactly right. The algorithm is correct. The algorithm done its job. Where is the flaw? You made the wrong assumption. You designed a correct algorithm, but you made a wrong assumption in constructing the algorithm. See, assumptions are pillars of the algorithm, building. You make a building, and they rest on foundations, right? Suppose you build the building very nicely, but the foundation is weak. Still the building collapses. There's nothing wrong with the builder of the building, but the person who put the foundation made a mistake, so they caused the whole building to collapse. Okay, so the algorithm assumptions are foundations. Okay, so the algorithm done its job, correct. The algorithm is functionally correct, but he made the wrong assumptions. So I had to change my assumptions there. Okay, so what do? So I ask a question for which I already know the answer, but I pretend that I don't know the answer. So I ask 100 questions and then see how many people are responding. I kind of do an analysis and then see how many people are bad. Because I know the correct answer, but I pretend that I don't know the answer. I ask different questions and things like that, and I find who is telling the correct answer, who is telling the wrong answer, and I kind of an idea of how many are bad guys. Then I increase my parameters. I cannot change you, but I can change the control parameter in the algorithm. That's like an autonomic adjustment, so that I don't make the mistake again. That's the idea here. And then I evaluate, this is a mathematical way of evaluating the system there. Again, depends on the mission criticality. Suppose in this particular scenario, it may not be a big deal. Okay, you say I saw a bird, maybe a crow you saw. I thought it was an eagle. What the heck, Even if I make a mistake, nothing wrong is going to happen. So I just, I don't want to deploy too many time and then asking about whether you saw a bird or an eagle, right? Whereas if it's a military setting, then it's important. Whether it's a missile is coming or a plane is coming, then that difference is important. So then I can afford to spend all the resources to correctly detect that. Whereas to detect between crow and eagle, no, I don't want to spend the resources that way. So that is the kind of thing that this is the, I'll stop at this point, so that, so it's like a control system. Okay, you have a group of drones flying, and some of them are malicious, but you don't know whether malicious or not, right? Because they all report something. And I don't know the ground truth. I don't know what's flying thousands of miles away. Like the Commander General of the US, he resides in Washington, D.C., but the theater of operations is in some other country. The commander is not physically seeing what's happening there. It all goes by reports, like radars, satellite GPS, or satellite data. All those things are collected and then processed, and the commander makes a decision. The commander never sees a plane and in the enemy turret, right? But he's a decision maker. He's the one who pushes the button. And he wants to make sure that he pushes the correctly, right? So the drones don't make decisions. Drones only report. The decision making is done by and how often you make correct decisions. And that's the quality here. So the quality of surveillance reports, it collects, and you can test them using model checkers. You pretend that there is an enemy object and see how the drones detect them. Okay. And then you collect surveillance reports, and again, you have operational models, prototypes. So prototyping is expensive because to detect objects in the terrain, I had to deploy drones in a lab setting. And that's expensive and it takes time. So I fly a bird within a lab, okay, and then see if the drones detect it. So that once the software is tested, then you can deploy the drones in the real world. But I had to develop the lab prototype for a couple of years. But the military wants it within 2 months. So you had to, that way, these probabilistic model checkers will come in handy. So this is the idea here. This is takes a middle ground. This is very accurate, but it takes a long time. This is too inaccurate. Whereas this takes a middle ground, and then you deploy the more drones, the algorithm parameters you can change based on evaluating the conditions, and then you adjust them here. Okay. You test the system, and then see if the test system detects objects correctly, and then based on the probability of failures. So I'm always going to make mistakes. 99%, or if I say 98% detection probability, that means 2% of the times I failed. So whether I can afford to waste 2% of the time, fail. In a military setting, that's not acceptable. But in a normal, suppose I watch scenarios, watch natural scenery, what the heck, instead of seeing a tiger, I thought I saw a lion instead of a tiger. Okay, what the heck, nothing is going to happen. So I don't want to spend my resources on where the mission is not critical. You see the point here? So that's the kind of thing there. And the model checkers helps here. And maybe one last slide. I'm just skipping a lot of them here. Again, an operational model looks like this. It's all a set of equations. I'm not going to get into how the equations are derived. It's all probabilities. Okay? And we have results and things like that. But these are inaccurate. But they're good enough. See, inaccurate doesn't mean that they're bad. They're good enough for me. Okay? The other one is we did develop the software in the lab, the Linux lab at CUNY. It took like 2-3 years to develop that software. 4 PhD students, 3 MS students. Okay. Now this is about probabilistic model checking, where you use state transition approaches. So I'm going to just show one thing here. Again, let's skip all these things here. Sorry, what happened here? Oh, what happened? Okay. Okay, so this is the main thing there. Now, so these are good guys. Okay, so you write the good guys as well as you program the bad guys too. So it's like a policeman thinks like a thief in order to catch a thief. The policeman is not a thief, but the policeman has to think like a thief, so that he knows where the thief will hide. He knows where the thief will act upon, so that he can put the right force, deploy the right forces, right? Thinking like a thief doesn't make you a thief, right? A policeman is a good example, right? So I had to program both a thief as well as the policeman who thinks like a thief. I had to program both the guys. And both are state transition. The computer software doesn't know who's a thief. A thief can justify whatever his action doing. A pickpocket just has his own way of justifying what he's doing, right? And as a good guy, you also have a way of justifying what you don't want to lose money. But the pickpocket justifies his action because he needs money for, something, whatever it is, right? So he had to, this one here. Now the bad guy also we write as a program, okay? That's a program that collects, there's a set of libraries we keep, and you can plug in, play various Byzantine attacks, computation straggling. Straggling means you deliberately do slow. You ask me a question, what is 2 plus 3? I give you the answer after 1 hour. It has to be in half a second, right? But you say ask 2 plus 3, I have to respond in even half a second is lot, right? Suppose it take 1 hour to respond to you. I gave you the correct answer, but that's of no use. It's called a computation straggling, okay? So the bad guys can behave in many ways, okay? And this bad guy tells this software, you guys have to behave badly, you guys have to behave good. It's a probabilistic notion. A bad guy never behaves badly all the time. Okay, that's easy to catch. A bad guy behaves maybe 1 in 50 times. 49 times he is behaving good, so that he cannot be caught. Okay, that's the idea here. And there's probabilities can be controlled here. Okay, and there is a good guy. All of them run in the mind. See, in my mind, there is one part of the brain acts like a bad guy, another part of the brain acts like a good guy, and the third part of the brain acts like a neutral guy who says whether the good guy wins or the bad guy wins. And there's a fight between the good and bad part of the thing there, and typically the good part wins, right? And we have utility functions, other things to make the good part of the thing. Otherwise, the thief is also a human being. He has a brain, and one thing works in the wrong direction, right? But at a modeling level, you kind of model everything there, and that's pretty much it is. It's a state transition analysis, and then that's it, yeah. So this is a kind of last slide. So this is how the model checker libraries work here. What happens is you have algorithms. The language doesn't care who is good and bad. Good and bad is your definition. For me, this is good, but the same thing will be good or bad for you. Okay. Likewise, the other way. Now, what you think is good can be quoted as libraries. And these are the environment libraries. If you take a supply chain as an example, you can simulate road outages. Suddenly there is road outage, the petrol doesn't come on time, or the products doesn't come on time, which means there's a shortage there. Well, what's the impact of the shortage on the society? Okay, you can analyze it. Maybe this is an important item. People run out of the item in the stores, so that causes a social friction, those kind of things there, right? You can simulate them without actually causing a shortage. You can simulate the shortages without creating a shortage and see how you'll react so that the manager makes the best decision. Okay, and this is the last slide. And just likewise, now you can change the algorithms there, and these are all you can plug and play. And the software model checker plugs and plays different algorithms, all runtime, all within a few milliseconds. And this software can run in a data center in Australia and send the results to the decision maker who is in Bangalore. You see, it's a very challenging computational task. Okay, so that I can evaluate the quality of my decision making, and I can stand by the quality of decision making. I can make correct decision 99% of the time, 98% of the times. And how do I make that statement? I have tested this in the lab, in this software, and I can control the probabilities and do that here. So I'll stop at this point. Okay. Again, there's a number of slides there, but I will send you some papers. It's all about trustworthiness. So Janet Wing of Carnegie-Mellon, she says, any intelligent decisions are probabilistic. You make intelligent decisions, but they may fail 1 in 100 times. Because you fail to look at certain events. And that event unfortunately happened. And then you just think, right? So being careless is one thing. fail to overlook certain things. Suppose there is a rain prediction there. I didn't take an umbrella, I get drenched. That's my fault, right? Yes. But these kind of things are there. But you can kind of plan these consequences with this one here. And you can change these algorithms, errors dynamically, and then you can evaluate how good you do. Because I always say, pessimism and optimism are two sides of the same thing there. You can be a pessimist all the time, but there's only a finite number of years you live. I don't want to spend 40 years of my life being a pessimist, worrying about what's going to happen on this time, what is going to. We have to be careful, no doubt about it. Yeah. But over pessimism is bad. At the same time, over optimism is bad, right? So sometimes I keep cash two places. I have cash some here and cash in the bag also. Why? What if if there is a hole in the pocket that still I have money left to go home, right? We all do that kind of thing, right? But if I'm overcautious, that overcautiousness affects the quality of life. So that's the kind of a message. And this probabilistic model checking allows you to strike a neutral ground. You make correct decisions, but not being over pessimistic, not being over optimistic. You make the right level of decisions, and you can enjoy the life, particularly in today's AI and ML worlds. Okay, I'll stop at this point. Again, the slides are available with the, so you can kind of look at the slides. And we are kind of currently doing this. We have a couple of PhD students doing this work. Yeah, it took quite a while. Yeah, sorry.
Let's all thank the speaker.
Okay.
Thank you very much, Professor, for
You're
accepting
welcome.
our invitation and giving a wonderful talk. In the interest of time, we request the audience to take questions at the coffee hut while having the arranged refreshments. Thank you all for attending and have a great day.
Yeah, are there any Zoom attendees? Okay, yeah, okay. That's good, yeah. Okay, thank you. Yeah.